Bismillahirrahmanirrahim. In this video, we are going to solve numerical problems of the chapter Feedback and Oscillator Circuits. The author of the book is Robert Bolysted. The book name is Electronic Devices and Circuits. So we are going to solve the numerical problems. The book we have is the 10th edition book. Number 1 is calculate the gain of a negative feedback amplifier having A is equal to minus 2000. This is gain without feedback, and beta, which is the feedback factor, is equal to minus 1 divided by 10. So we need to find the gain with feedback. For that we know that gain with feedback denoted by AF is equal to A divided by 1 plus beta A. So we only need to put in the values. A is minus 2000, which is gain without feedback. We have 1 plus beta is minus 1 by 10 again into A, which is minus 2000. So this comes out to be minus 2000 divided by 1 plus, this will be cancelled out with this, and we are going to have 201, and this comes out to be minus 9.95. So the gain with feedback is minus 9.95. Let us solve question number 2, problem number 2. Problem number 2 states that if the gain of an amplifier changes from the value of minus 1000 by 10%, calculate the gain change if the amplifier is used in a feedback circuit having beta is equal to minus 1 by 20. So this problem is from the topic gain stability with feedback. Gain stability with feedback. Okay, now we have gain without feedback given, which is minus 1000, fine, and we have the change of gain without feedback also given, which is 10%, and beta, the feedback factor, is also given. So we need to find the gain with the feedback, the gain change with the feedback, and the gain change with the feedback is denoted by df divided by af. Now we know that this equals to 1 divided by beta a, the magnitude of 1 divided by beta a, dA divided by a. Here dA divided by a is the magnitude of the relative change of gain without feedback, and this is the magnitude of the relative change of gain with feedback. So we need to find the magnitude of the relative change of gain with feedback. The magnitude of the relative change of gain without feedback is given as 10%. Fine. So let us put the values. Beta is minus 1 by 20, and then we have A, which is minus 1000. Then we have dA divided by A, which is 10%. So we have 1 divided by 50 multiplied by 10%, which comes out to be 0.2%. So this is magnitude of relative change of gain with feedback, which is 0.2%. So this improvement is 50 times, because the magnitude of relative change of gain without feedback was 10%, but now the gain change has been reduced, and it has been reduced to 0.2%. So the improvement is 50 times. Let us solve problem number 3. And in problem number 3, we need to find the gain, the input impedance, and output impedance of a voltage series feedback amplifier having, again, this A denotes the gain without feedback, and input impedance or input resistance is given, output resistance is also given, and beta is also given. Now we know that gain with feedback in case of voltage series feedback, or in case of any feedback, that is equal to AF is equal to A divided by 1 plus beta A. Now here A is given, which is minus 300, and we have 1 plus beta is also given, which is the feedback factor, that is minus 1 by 15, and then we have again A, which is minus 300. So we have minus 300 divided by 1 plus beta A. So 15, this 20 is your 300. Fine, because 15 2s are 30 and 0 is over here. And minus into minus will be plus. So we have 1 plus 20, that is 21. So we have 1 plus beta A is equal to 21. And if you solve this, you are going to get minus 14.3. So we have found out the gain with feedback. Now we need to find the input impedance at the input resistance with feedback, that is ZIF. Now because this is voltage series feedback, we know that the series feedback tends to increase the input impedance. So that's why on input side we are going to have Zi into 1 plus beta A. Zi or Ri is given, which is 1.5 kilo ohm. Multiply by 1 plus beta A. We have already found the 1 plus beta A value, which is 21. So we need to multiply 21. We are going to get 31.5 kilo ohm. Now we need to find the output impedance. Now because we have voltage feedback, and I stated earlier that voltage feedback reduces output impedance. The series feedback increases input impedance, the voltage feedback reduces output impedance. Output impedance is going to be reduced. Z0 1 plus beta, Z0 R0 1, and the same thing. Again 50 kilo ohm is your Z0, and 1 plus beta has already been calculated, which is 21. So 50 divided by 21, we get 2.4 kilo ohm. So this is your output impedance of this voltage series feedback. Let us move to the problem number 4. In problem number 4, it states calculate the gain with and without feedback for the FAT amplifier as in figure 18.7, and 18.7 is your this figure. For circuit values given, R1 is 800, R2 is 200 kilo ohm. Fine, this is 200 kilo ohm. Not 200 ohm, but this is 200 kilo ohm. R0 is given, RD is given, and transconductance GM is also given, which is 5000 microsiemens. Now what we need to find? We need to find gain without feedback and gain with feedback. Fine. So first of all, for the FAT amplifier, and this FAT amplifier is a common source amplifier. Its gain is equal to A is equal to minus GMRL. Now in this case, what will be the RL? For RL, we need to perform this AC analysis. For AC analysis, this VDD is going to be grounded. So for AC analysis, this VDD is going to be grounded. This capacitor is going to be shorted out. So this we are going to have a short over here, and we are going to have a ground over here. Now when this happens, we are going to have R1, R2 parallel to the R0 parallel to RD. So we are going to have R1 plus R2 parallel to R0 parallel to RD. Now this is basically your resistance RL. So RL here is equal to R1 plus R2 parallel to R0 parallel to RD. Now if you see R1 plus R2, R1 is 800 kilo ohm, R2 is 200 kilo ohm. This sum is very greater than R0 and RD. R0 is your 40 kilo ohm, RD is your 8 kilo ohm. And we know that in parallel combination, the highest resistance does not affect the value that much. So we can take approximate value, and we can say that RL is approximately equal to the parallel combination of R0 parallel to the RD, and this is equal to R0 parallel to the RD, which means 40 kilo ohm parallel to 80 kilo ohm. So this is 40 kilo ohm multiplied by 80 kilo ohm divided by 40 kilo ohm plus 80 kilo ohm. And when we solve this, we are going to get the value of the RL, and this RL comes out to be 6.7 kilo ohm. Right? This is just the parallel combination formula. R0 multiplied by RD divided by R0 plus RD. So this comes out to be 6.7 kilo ohm. So now the open loop gain is equal to minus GMRL, where GM is the transconductance. So we have 5000 micros 10 raised to power minus 6 multiplied by this 6.7 kilo ohm. And when we solve this, we are going to get gain without feedback as minus 33.5. So this is your gain without feedback. We have found out one of the parameters, that is gain without feedback has been found out. Now let us find gain with feedback. Now to find the gain with feedback, we need to find the feedback factor beta, which in this case will be equal to minus R2 divided by R1 plus R2, because beta is Vf divided by V0, and using the voltage divider rule, this is your Vf and this is your V0. So Vf will be equal to R2 divided by R1 plus R2 with the negative sign. So now we put the values. minus R2. R2 is the value of R2, 200 kilo ohm. R1 is your 800 kilo ohm. So we have minus 200 kilo ohm divided by 200 kilo ohm plus 800 kilo ohm. Fine. And this comes out to be minus 0.2. Now once the beta is found out, we can find the voltage gain with feedback, that is equal to A divided by 1 plus beta A. Here A is the gain without feedback, which has been found out to be minus 33.5. The beta is also being found out, which is minus 0.2. So we need to solve this, and when we solve this we get minus 4.4. So this is gain with feedback for this FAT amplifier, and the gain without feedback was minus 33.5, and the gain with feedback is minus 4.4. Okay, next is problem number 5. It says that for a circuit in figure 18.11, and this is your circuit of figure 18.11, and the following circuit values. Calculate the circuit gain and the input and output impedance with and without feedback. So we need to find the gain without feedback and gain with feedback. Similarly, we need to find the input impedance with and without feedback and the output impedance with and without feedback. And we have resistance RB is equal to 600 kilo ohm, RE is 1.2 kilo ohm, RC is 4.7 kilo ohm. Beta, this is your current gain beta, which is 75, and VCC, which is the DC supply, is 16 volt. So we need to find the gain with and without feedback, input impedance with and without feedback, and output impedance with and without feedback. Now this circuit is your common emitter configuration, and remember that this is your current series feedback circuit. This is your current series feedback circuit. Current series feedback circuit. So we need to have this in mind while finding the input and output impedances with feedback. So first of all, we need to perform the DC analysis because we need the current IB. For the DC analysis, if you look at here, this VCC is connected with the resistance RB. This RB is your 470 kilo ohm in this case, but in this case it is, you look at here, in this case this is your 600 kilo ohm. This is your RB basically. So we have VCC RB. This capacitor is going to be open circuited, so we are going to have an open circuit over here. Fine. And then we have the VCC RC, and RC value is also given over here, that this RC value is 4.7 kilo ohm. This is again your VCC. Same, this is your RB, this is your RC. Fine. This is connected like this, and then we have the resistance RE, and RE is your 1.2 kilo ohm. Fine. This is connected to ground. We have a connection over here, and that will be open circuited. Fine. So what we need to do, and we know that this in this RB circuit we are going to have the current IB flowing over here, and this RE circuit we are going to have current IE flowing over here, and this is your base to emitter junction, which is the VBE. So let us find current IB using this portion. So we have, using this portion, this portion. So if I redraw this circuit, I have a VCC. This is my plus minus VCC. Then I have the resistance RB, and this RB value is given to me, which is RB value is given, which is 600 kilo ohm. Right? This is your 600 kilo ohm. And then we have a transistor. We have the base to emitter junction. This is your VBE. And then we have a resistor RE. And this RE is 1.2 kilo ohm. and we have current IE flowing over here. And this is connected to ground. This is also connected to ground. So I can connect these two together to the ground. I can say that some current is flowing over here. So let us apply the uh, KVL over here. VCC is your voltage rise. So we have VCC. This IB current flows. So this is your IB RB, and this is your drop. This VCC is your rise. We are going to write it again. VCC is your rise is positive, and this is, let me write the drop on the other side. IBRB is your drop. Similarly, the VBE, this is your base to emitter junction. This is also your drop. And then this IERE, this is also your drop. So we have this equation. Fine. And I can rearrange it and say that VCC minus VBE is equal to IB RB. Let me write it again. IB RB plus IE RE. So we have lengthy maths, but it's very easy. Fine. So I need to find the IB. So I can write this as VCC minus VBE and then IB RB, and we know that IE is equal to beta plus 1 IB. I can write this as beta plus 1 IBRE. Now from here I can find IB. I can say that IB is equal to IB, I'm going to take common from here, that IB is equal to VCC minus VBE divided by, find this is your RB, not RE. Find this is your RB. Right? This is RB plus theta plus 1 RE. Find. Here I have taken IB common from here. Take IB common from here, and the rest will be divided over here. So I am going to put values. VCC is given to us, which is 16 volts. So this is 16 volt. VBE is your base to emitter junction, which is 0.7 volt. You know that. RB is given to you, which is 600 kilo ohm, and beta is also given to you. Beta is your current gain, and in this case it's 75. So beta plus 1, so it is 76. 76 into RE. RE is your 1.2 kilo ohm. Now if you solve this, you are going to get IB is equal to 22.1 microampere. So we have found out the base current, which is IB. Now when we found out the IB, we can easily find the IE. So let us, now IE is your, I'm going to write over here, IE is your beta plus 1 IB. We know that. And beta is your 75, so this is 76 into IB, which is 22.1 microampere. And if you solve this, you are going to get 1.68 milliampere. So we have IE found out, which is 1.68 milliampere. Fine. Let me write the rest over here. So we have found out the IE. IE is your 1.68 milliampere. Fine. Now from this we can find the RE. So RE, we know that 26 millivolt divided by the IE, and IE is your 1.68 milliampere. So this is 1.68 milliampere. And if you solve this, you are going to get 15.5 ohm. So this is your RE. Now why do we require RE? Because to find the input impedance without feedback, that is the ZI, that which is equal to HIE in hybrid parameters, which is the input impedance without feedback, that is equal to 1 plus beta into RE. Here beta is again the current gain, which is the 75. So this is basically 76 multiplied by 15.5. And this comes out to be, this input impedance, this HIE, this comes out to be 1.18 kilo ohm. Fine. So when we multiply the 76 with 15.5, we are going to get 76 multiplied by 15.5. We are going to get 1178. So this is 1.18 kilo ohm. Fine. And now Z naught is easy to find. Z naught will be equal to or approximately equal to the RC. And RC is given to you that this is 4.7 kilo ohm. RC is given to you. You see this question, RC is given to you that RC is 4.7 kilo ohm. So we have found out the input impedance without feedback and the output impedance without feedback. Now to find the gain without feedback, the voltage gain without feedback, that will be equal to minus HFE divided by HIE plus RE. This equals, now we have found out the minus HFE. HFE is your beta basically. What is your HFE? HFE is your beta because small signal current gain in hybrid parameters is HFE. We know that. So we are going to have minus 75 plus the HIE which we found out, which is the input impedance 1.18 kilo ohm. And then we have the RE which is given to you, which is 1.2 kilo ohm. So this comes out to be minus 31.5 multiplied by 10 raised to power minus 3. Right? So this is the gain without feedback. This is not the voltage gain, but this is the gain for the current series feedback. Your output is current and the input is voltage. So we have found out the without feedback portion. Now for with feedback portion, we have first of all beta. Beta is equal to minus RE. And this is equal to minus 1.2 multiplied by 10 raised to power 3. Fine. Because RE is your 1.2 kilo ohm. And then we have the AF is equal to A divided by 1 plus beta A. Where A is your this thing which is minus 31.5 multiplied by 10 raised to power minus 3. 1 plus beta is your this thing minus 1.2 multiplied by 10 raised to power 3. Into A again, which is again this thing minus 31.5 multiplied by 10 raised to power minus, this is minus 3, yes this is minus 3, right? So we are going to get gain with feedback, that will be equal to 811.86 multiplied by 10 raised to power minus 6, right? So this will be your gain with feedback. So this is your gain. Now if you want to find the voltage gain, that will be equal to minus AF multiplied by the RC, and RC is again given to you. So if you simplify this, you are going to get minus 3.82, right? So we have found out the gain with feedback. Now what about the input impedance? Because we have a current series feedback combination, we have a series feedback. The series feedback increases the input impedance. So this will be Zi 1 plus beta A. 1 plus beta A, this factor is equal to your 38. Fine. This factor is equal to 38.8. So what we are going to do is that Zi is, again we have found out the Zi, that was somewhere around here, that we have found out the Zi. Here it is. Zi is your 1.18 kilo ohm. Fine. So what we need to do is that Zi is your 1.18 kilo ohm. That will be multiplied by 1 plus beta A, which is 38.8. Fine. And this comes out to be 45.8 kilo ohm. This is your input impedance with feedback. Finally, the output impedance with feedback. Again, we have current series feedback. We have current feedback. Output impedance will be increased. So we are going to have Z0 1 plus beta A. And Z0 has already been found out. Z0 is output impedance without feedback. That is equal to 4.7 kilo ohm. Fine. So that is 4.7 kilo ohm. That is equal to RC. We have 38.8. When we solve this, we are going to get 182.4 kilo ohm. So this is your output impedance. So we have found out what was required. We found the output impedance with and without feedback, the input impedance with and without feedback, and gain with and without feedback. Okay, problem number 6 states that an FET phase shift oscillator having GM, which is the transconductance 6000 microsiemens, RD is equal to 36 kilo ohm, and feedback resistor R is equal to 12 kilo ohm is to operate at 2.5 kilohertz. So let's see for the specified operation. Now we know that for the FET phase shift oscillator, the frequency is given as F is equal to 1 divided by 2 pi under root C under root 6 into RC. So this is the equation for the frequency. Now the frequency is given, we need to find the C, which is the capacitance. So C is equal to 1 divided by 2 pi under root 6 R into F. Find this R is not in under root. So we are going to put values. So we have C is equal to 1 by pi is 3.14, and then we have the under root 6. Then we have multiply by R is your 12 kilo ohm, so that is 12,000. And then we have the F, which is the frequency, which is 2.5 kilohertz. So that will be multiplied by 2.5 kilohertz is 2500. So we are going to multiply this. When we multiply this, we are going to get 1 divided by 461,483, 862 or something. Fine. And when we take the reciprocal, when we solve this, we are going to get 2.167 multiplied by 10 raised to power minus 9 farad, because it's capacitance. So we are going to have 2.167 nanofarad. So C is equal to 2.167 nanofarad. That is our answer. Now next question, which is the problem number 7. Problem number 7 states that calculate the operating frequency of a BJT phase shift oscillator. The sixth problem was related to FET phase shift oscillator. This is related to the BJT phase shift oscillator. For R is equal to 6 kilo ohm, C is equal to 1500 picofarad, and RC is equal to 18 kilo ohm. Now we know that the frequency for the BJT phase shift oscillator is given as, we have discussed this in our previous videos, that the frequency is equal to 6 plus 4 RC divided by R. Fine. So we are provided with everything, we just need to put the values. We are going to have 1 divided by 2 pi. R is given to you, R is 6 kilo ohm, which is 6000. So this is 6000. And then C is also given to you, which is 1500 picofarad. Pico is your 10 raised to power minus 12. Fine. Now and then we have 1 divided by under root 6 plus 4 RC divided by R. RC is your 18 kilo ohm and R is your again 6 kilo ohm. This RC by R is your 3. Fine. So this is your 3. And for 3s are is 12, and we are going to have 12 under root 18. So this portion is 1 divided by under root 18. So we are going to have 1 by 2 pi multiplied by 6000 multiplied by 1500 multiplied by 10 raised to power minus 12 into 1 divided by, this is your under root 18. And when we solve this, we are going to get the frequency. And the frequency in this case will be 4.17 kilohertz, which means approximately equal to 4.2 kilohertz. So we have found out the operating frequency of the BJT phase shift oscillator, which is 4.2 kilohertz. This is your answer. Now next is your problem number 8. In this problem, we are going to calculate the frequency of the Wien bridge oscillator. when R is equal to 10 kilo ohm and C is equal to 2400 picofarad. Again, the frequency of the Wien bridge oscillator is given as F is equal to 1 divided by 2 pi under root R1C1 R2C2. But since we are given with only R and C, it means that R1 is equal to R2 and C1 is equal to C2. So if in that case, then the frequency becomes equal to 1 by 2 pi R. So you just need to put the value. So we are going to have 1 divided by 2 pi, which is 3.14. R is your 10 kilo ohm, that is 10 kilo ohm is 10,000. So that means that we are going to have 10 raised to power 4. Fine, and C is 2400 picofarad. Again, pico is 10 raised to power minus 12. So we are going to have 1 divided by 2 into 3.14, and this 10 raised to power minus 12 will be multiplied by 10 raised to power 4. So we are going to have, also we have 2400. So this will be 2400 multiplied by 10 raised to power minus 8. This term can be also written as 2.4 multiplied by 10 raised to power minus 5, one and the same thing. And so when we solve this, we are going to get F is equal to 6.634 kilohertz. Because this term is equal to, I'm going to write over here, this is equal to 1 divided by 0.00015072 or 672. 072. So when we solve this 1 divided by this thing, we are going to get the frequency of oscillation, which is 6.634 kilohertz. Okay, problem number 9 states that for an FAT Colpitts oscillator, the following circuit value is determined the circuit oscillation frequency. C1 is equal to 750 picofarad, C2 is equal to 2500 picofarad, and L is equal to 40 microhenry. Now we know that the frequency of the Colpitts oscillator is given as F is equal to 1 divided by 2 pi under root L C equivalent. Here C is the equivalent capacitance. Now this equivalent capacitance C, this was equal to C1 C2 divided by C1 plus C2. Now C1 is given 750 picofarad, so we have 750. C2 is your 2500. And then we have 750 plus 2500. So we are going to solve this, and end result is going to be in the picofarad because C1 and C2 are in picofarads. So when we solve this, we are going to get 577 picofarads. So C equivalent is equal to 577 picofarad. Fine. So now let us put the value. So we have F is equal to 1 divided by 2 pi. 2 pi is your 6.28 because pi is 3.14. And then we have the under root. And in under root we are going to have L, which is 40 microhenry. So 40 multiplied by 10 raised to power minus 6. And multiply by this 577 picofarad. So 577. This is 577 multiplied by 10 raised to power minus 12. Fine. So just we need to solve this. We are going to get 1 divided by 6.28. And 40 multiplied by 577 is your 23080. So we are going to have 23080. And we have 10 raised to power minus 6 multiplied by 10 raised to power minus 12. So both will be added. We are going to get 10 raised to power minus 18. So we are going to have 1 divided by 6.28, and the under root of 23080 is 151.92. So we are going to have 151.92, and this 10 raised to power minus 18 under root will become 10 raised to power minus 9. Fine. So it means that if I shift this to the numerator side, we are going to get 10 raised to power 9 divided by 6.28 multiplied by 151.92. That comes out to be 954.06. So we are going to have, okay, so I can say that 1000 divided by 954.06, 1000 is 10 raised to power 3 multiplied by 10 raised to power 6, because 10 raised to power 3 and 10 raised to power 6 is 10 raised to power 9. And this 1000 divided by 95408 is your 1.048 multiplied by 10 raised to power 6. So this is your frequency. So I can say that f is equal to, or f naught is equal to 1.048 megahertz, because it's frequency, so we are going to have a unit of hertz, and 10 raised to power 6 is mega. So this is your frequency of oscillation of this Colpitts oscillator with the following C1, C2 values and the inductor value of 40 microhenry. Now let us solve the problem number 10. Again we have the Colpitts oscillator, and again we need to find the frequency. So we have the transistor Colpitts oscillators, and the circuit values are given. L is 100 microhenry. Radio frequency coil is 0.5 millihenry. C1 is 0.005 microfarad. C2 is 0.001 microfarad, and CC is your 10 microfarad. Now again the formula is given as f naught, or f is equal to 1 divided by 2 pi under root L C equivalent. So again, first of all, we need to find the C equivalent, and C equivalent is again C1 multiplied by C2 divided by C1 plus C2. So we are going to have C1 is your 0.005 multiplied by C2 is 0.01. Again, the addition of both two, that is 0.005 plus 0.01. And when we solve this, we are going to get 0.00333. Now because this is in microfarads, the answer will be in microfarads. Now I can write this number, because we are going to have 6 digits over here. I can write this as 3333 picofarads, because pico is 10 raised to power minus 12 and micro is 10 raised to power minus 6. So I can write this microfarad number as 3333 picofarad. Fine. Because to convert micro to pico, we are going to move 6 digits right. The point is over there, we are going to move 6 places to the right. So we have moved the 6 places to the right. So we are going to have C equivalent of this value. Now once the C equivalent is known, we can simply put the values, because all other are given. So let us simply put the values. F naught equal to, again 2 pi is 2 multiplied by 3.14, which is 6.28. And then we have the under root, and under root L is given to you. L is your 100 microhenry. So that is basically 100 multiplied by 10 raised to power minus 6. And then we have the C equivalent, which has been found out, and that is 3333 picofarad, which is 10 raised to power minus 12. Fine. So we are going to solve this, that F naught is equal to 1 divided by 6.28. Okay, this 100 multiplied by 10 raised to power minus 6 will be 10 raised to power minus 4. Why? Because 100 is 10 raised to power 2. So this term will be 10 raised to power minus 4, and we have 10 raised to power minus 12 over here. So total will be 10 raised to power minus 16. So we are going to have 3333 multiplied by 10 raised to power minus 16, because minus 12 and minus 6 is minus 18, and we have plus 2 over here. This is 10 raised to power plus 2, so that is 10 raised to power minus 16. So we are going to have F naught is equal to 1 divided by 6.28, and under root 3333 is your 57.732. So this is 57.732, and 10 raised to power minus 6 under root is 10 raised to power minus 8. So we are going to have these values. And now what we are going to do, so I can write this as, because when I move this to the numerator, it will become 10 raised to power positive 8, and divide by 6.28 multiply by 57.732, which is equal to 10 raised to power 8 divide by, and when we multiply these two, we are going to get 362.55, 362.55, which comes out to be 2758 kilohertz. Sorry, not 2758 kilohertz, but this is 275824 hertz, which is basically 275 kilohertz or 276 kilohertz. So that is the frequency of oscillation, 275 kilohertz for these values given. Okay, problem number 11 is related to Hartley oscillator. It says that calculate the oscillator frequency of an FAT Hartley oscillator for the following circuit values. C is equal to 250 picofarad, L1 is equal to 1.5 millihenry, L2 is 1.5 millihenry, M is equal to the mutual conductance is 0.5 millihenry. Now we know that the frequency of oscillation of the Hartley oscillator is given as 1 divided by 2 pi under root L equivalent into C. Okay, now this L equivalent is equal to L1 plus L2 plus 2M. Now L1 is given to you, which is 1.5 millihenry, L2 is also given to you, and L2 is also 1.5 millihenry, and then we have M, which is 0.5 millihenry. So this is 3 plus, and 2.2 multiplied by 0.5 is 1, so this is 4 millihenry. So this is your L equivalent. Now once L equivalent is known, we are going to find the L equivalent is your 4 millihenry, which is 4 multiplied by 10 raised to power minus 3, and this is multiplied by 250 picofarad, and 250 picofarad is 10 raised to power minus 12. Fine. So this is F is equal to 1 divided by 2 pi is 6.28. Okay. Now 4 multiplied by 250 is 1000, and 1000 multiplied by 10 raised to power minus 3 is 1, because 1000 is also 10 raised to power 3. So 10 raised to power minus 3 and 10 raised to power 3 will be cut out. So we are going to have under root 10 raised to power minus 12, which means that we are going to have 10 raised to power minus 6, and I can move this 10 raised to power minus 6 to the numerator. We are going to have 10 raised to power 6 divided by 6.28, and this comes out to be 159.2 kilohertz, because it's frequency, so we are going to have hertz, so this is 159.2 kilohertz, and that's the frequency of oscillation of this Hartley oscillator. Now in 12, again we need to find the frequency of the Hartley oscillator. Again same formula, F is equal to 1 divided by 2 pi under root L equivalent into C, and L equivalent is again L1 plus L2 plus 2M. So here L1 is 750 microhenry, L2 is also 750 microhenry, and then we have 2M, which is 150 microhenry. So 750 plus 750 is 1500, and this 2 into 150 is 300. So 1500 plus 300 is your 1800 microhenry. Fine. So put it over here. We are provided with everything. L equivalent is your 1800 microhenry, which is 1800 10 raised to power minus 6, multiply by C. C is your 150 picofarad, which means 150 multiply by 10 raised to power minus 12. So solve this because 2 pi is 6.28, and when we solve this, we are going to get the frequency of oscillation is 306.3 kilohertz. So this is your frequency of oscillation of this Hartley oscillator. Question 13 is theoretical question. Question 14 or problem number 14 is not in our course, is not included in our course. So that's all for today. Thank you.